Hi guys, welcome to my YouTube channel, and in today's video we will be discussing about Amazon DynamoDB, right? And then we will understand the internals of DynamoDB. We will also understand how the get and put operations gets work, and we will also understand what are the techniques that are being used in the DynamoDB internals, right? So let's quickly begin with it, right? So if in case you know about DynamoDB, you may or may not have been aware of the DynamoDB, but I'll quickly tell you that it's a very high availability storage system which supports key value, right? So you insert the data in form of key value in DynamoDB, and it's very high availability system. What it means is that your the system will always be available for your write operations no matter what happens. Let's say any network partition happens between two nodes, right? Any server node failures happens among the group of nodes. No matter what happens, it will always be ready in the situation to accept your write operations, and that is why it's very popular nowadays, because it supports high availability, right? So now let's move on and understand few things about DynamoDB. So as I said, that it's very high availability system, that no matter what happens, write updates are not lost even in case of network partitions or server failures, right? Let's quickly understand how it works and what do I actually mean by high availability in it, right? So let's go to our drawing. Okay, so before moving into the drawing part, doing a deep dive into it, first understand the part peer-to-peer cluster, right? And also understand eventual consistency. Actually, I should have used these 2 points before high availability, right? And then don't focus on key value store as of now. We will discuss about it in the end, right? So let's discuss about peer-to-peer cluster first, right? Let's first understand how the nodes architecture, how the internal of the node architecture builds in the DynamoDB, right? So now go back here. So the way your DynamoDB has been architected is, let's say you have these nodes, right? So this is node 1, this is node 2, this is node 3, and this is node 4, right? So these are 4 nodes. When I say node, that means servers, nothing else. Very simple, servers. These are machines, right? Now all machines are connected to each other, right? So these machines are connected to each other. Now you have a client here. Now this client sends a write request. Let's say it sends a write request to this guy, right? Now if you see this whole architecture, this is a leaderless architecture, right? And that is what it means, the peer-to-peer architecture, peer-to-peer cluster. So it's basically a cluster, right? It's all a cluster, and then it's a peer-to-peer. So these are peers to each other, right? So now this is also known as leaderless architecture, right? What it means, if you have gone through my 2 other videos, if you go to my YouTube channel and go to playlist section, go to system design, you will find L1 and L2 2 lectures, where in one video I have explained single master replication, another video I have explained multi-master replication, right? You can go over it, you will understand, okay, what is this replication, what is single master, what is multi-master. I'll quickly tell you. Single master means all the write operation will happen via one single server node, which is designated as master, and all that write operation that happens in master will be replicated among all other follower nodes, right? Multi-master, write operations can happen in all the nodes, in the leader nodes, designated leader node, and then those leader nodes will replicate the data among other follower replicas, right? This is third kind of replication, where there is no leader, write can happen at any node. That particular node needs to there may be some peering, right? There may be based on that based on that replication factor, that particular data will be replicated to n number of replicas, the other peers, right? So maybe this, when n1 gets returned, right, and then once this is returned, this may get replicated to n2, right? That is how it works. Or let's say during the client is writing that data to this guy, write x is equal to 5, and then this goes down, right? Now, but your write operation can be handled by each node. So this may get rerouted to this node, right? So you still have the write operation. That's how it maintains the HA quality, your high availability, right? So it's very small brief. We will move on, then you will get a more idea, right? So let's quickly move on. So now it says, so we understood what is peer-to-peer, right? If you see, I have already explained you this peer-to-peer design, right? It's leaderless design. And then we also understand how it maintains the HA and what is the HA quality, right? If anything goes wrong, network partition or server node failures happens, that's how it maintains the write operation will keep on going. Now, third point is eventual consistency. If you remember, I have already explained you. First, if you see this case, x is equal to 10 happens at n1 node, right, at this node. Now later on, not then and there, it's not synchronous operation. If you go back and watch my single master replication video, there was a synchronous replication I have explained, where a write operation only gets completed when the same write operation happened in the other replica follower node as well, right? Then only the leader node goes back to client and say, hey, the write operation gets completed. But this is not the synchronous operation, this is asynchronous. What it means is, let's say this is your n1 node, right? And then this is your n2 node and this is your n3 node. Your client has written w is equal to x is equal to 20, right? So client has written some data at n1 node, this node n1. Now it says, okay, the write complete. But later on, after some time, it will replicate that data to n3. So n3 will also have x is equal to 20, right? So you see, then and there it did not replicate the same data to n3. But later on, after some time, this system n3 also has the value of n1, whatever the value of the n1 written as part of this write operation, and then value of x at n3 is also 20. So you see this whole system, so this system was kind of inconsistent till the time only n1 had the x value is equal to 20. But after some time, the n3 also has value x is equal to 20. So that means the system become consistent eventually. In the end, it become consistent. So the concept is known as eventual consistency, right? So your system become consistent in the end. So that is your eventual consistency. So that is what I have written here, that the Amazon DynamoDB is an eventual consistent system, right? It maintains the eventual consistency. Now, second point, key value store. As I already said, that it stores the key and value data, right? You can store any JSON object or XML, any kind of format object, text-based format into your DynamoDB, which should be less than 1 MB, right? So each key and value, because you will be storing your data in form of key and value, right? So there will be key and that key will have a value, right? But the important part is, let's say you have object, you have a JSON object, let's say you have ID, you have name, and then you have your address. Now among these three attributes, you need to accept one key as the partition key. So let's say you selected that your ID field is your partition key. Now what does mean by partition key, right? It's very important, because you need to understand, in order to understand what, because this is your DynamoDB, it is kind of a hash table, right? It maintains key and value. So there may be some get and put operation, there could be multiple operation, but let's majorly focus on get and put operation. The way your get and put operation works will based on key. Now which key will it be in the value? So there should be some key, some unique identifier. So we will call that identifier as the partition key. Now why partition key and how partition key will be used to get the value for a particular key from among the nodes in the leaderless architecture, we will see into next lectures, right? So this part, let's wait for some time and let's move on to next slides, and then before the end of lecture we will understand how this works. All right, so now let's move on and understand the architecture. So I already told you, right, the way this guy will work is you have leaderless architecture in place, peer-to-peer. As I said, it's a cluster of multiple nodes. So let's say there is node A, node B, node C, node D, and node E. Client can write to any node, any of the node, right? So, or it is totally up to client. So there will be two way of writing into the Amazon DynamoDB nodes. We will be understanding it into next slide, but this will be the architecture and all these nodes are connected, right? Let's quickly move on. I already explained it you in, if you remember right here, I already explained you this concept, right? Just go back to the video and understand. Okay, so now let's move on and understand the execution of get and put. That's what I was telling you, that the understanding of partition key we will discuss in this lecture. So if you see, there are two strategies. One strategy is, because you have your nodes, right, group of nodes, and then you have your client. Now how client write that, do a write operation to your nodes? One way is, there will be a load balancer, right? Client will only sending the data to the load balancer. Load balancer will select a node. All right, so let's go back and understand in depth. Let's say you have these nodes, right? And then you have your client here. One way is, you have a load balancer here. Client will send the value of the write operation here, and load balancer, a generic load balancer, will pick any value, not any value, any node, sorry, right? So this is N1, this is N2, and this is N3, and then this is N4. So your load balancer will pick any node and write into it. Will not write into it, we will understand. So that's the catch. So you see, load balancer picked up this N1 node and then send this operation of write operation. Now what will happen? This is one way, but we will see now what will happen. Let's understand the second approach, right? Now second approach is, client will use a partition aware library, right? So I've used the term partition aware. So what it means, that if you see, this is all data partitioning happening, right? This is all partitioning. This is all partitioning. The way your data has been partitioned among several nodes, right? Because it's peer-to-peer, there are multiple nodes, and not each node will have all your keys, right? There will be some separation, there will be some limitations. So if we will understand in the last lecture, consistent hashing, we'll see how your keys will be distributed among the nodes, right? It's very important lecture, the last lecture. But for now, understand that in this case, your client will send that value to a generic load balancer. That load balancer will pick a node and send the write operation. Now what will happen next, we will understand. But before that, understand the second approach. You have client here, and then you have N1, you have N2, you have N3, and then you have your N4, right? In this case, client, the code implementation of client will be using some client partition aware libraries, right? So that means there will be some code implementation itself will have that, okay, which node to select. So client can select this node. Let's say client will pick the N1 node and send the write operation. Now what will happen is, for your partition key, if you remember and go back, right, I made this question mark. Now understand, that's the point. Now you see, now what will happen? So client is sending X data, right? And for assume in your X, you have ID field as your partition key. So ID field is your partition key. So you have a JSON object where you have ID, username, address, city, etc., etc., all those details, but you are assuming that ID is your partition key. Now what will happen is, it will use MD5 on your ID field. So it will generate 128-bit uniquely identifier. So let's say if you go back and see the next point, I say DynamoDB applies MD5 key, right? And it will generate a 128-bit unique identifier, which is used to determine the storage node for serving the key, right? So that's the catch. So that's the catch is, do you know the implementation how HashMap works, right? Because the way HashMap works is, you have these buckets, right? What are these? These are basically nothing but your buckets, and then this is, let's say, your K1. Now what happens in hash map is there is a hash map gets a hash function gets applied to your K1, and then it will tell you that at this particular bucket your data will be stored. So these buckets, but nothing but these are your nodes, right? And same thing happening here, right? So it's a hash MD5 function is being applied on your ID, and ID is what is your partition key. So that means MD5 is being applied on your partition key. It's generating a 128 bit identifier. So this identifier is telling at which node your data is going into. So that also means that, so what happening here is it's also applying as the hash function of ID, and then this will tell that the N1 is your node which has this particular key. So let's say N has your K1, K2 and K4, right? So it simply sends the value of K1 and V1, right? So that's how your the data or your that's how your get operation will work, right? And a put operation will also work. So get K. And then in same case it will work here as well. So what it does is it will perform the hash function on ID, and based on the hash function it say, okay, the N1 is my node where my K1 key 1 let's say my ID is equal to or anything, let's say, which is 14. So my hash 14 is present in N1, right? So it will reroute it to N1. So that's how there are two approaches. One, I said that your client will send your data to your generic load balancer, and second one is your client will directly is using a partition aware client library as part of code implementation. It will automatically select a correct node, right? Now one thing can happen is, let's say your generic load balancer picks up, let's go back, it's already very congested, and let's say this is your client, right? And then this is your N1, this is your N2, this is your N3, and then this is your N4. Okay, now it sends the X operation to LB, right? Load balancer says that load balancer picked up any node and sends your write operation to N3. Now the N3 is not the node which has your key, right? Now what it will do, it will simply because now that's the concept of preference list, right? So now before completing this diagram, let's go back and complete the slide so you will get an idea. Okay, so far we understood that there could be two approach. That one, the client sends the write operation to your load balancer, and load balancer will pick a node and perform the write operation if the node is the correct node to perform the operation. If not, then it will send it to the coordinator node. Now what is coordinator node and what is preference list, we will see now this part. And the second implemented strategy is client will use a partition aware library, and then it will pick up a node based on your library implementation, pick a node and perform the write operation, right? Let's say if it performs the write operation to N1, and later on that N1 the data gets replicated to your N3 as well. So your system will become eventually consistent. And the way it will work is it will apply a hash function MD5 on your partition key, and whatever the outcome will be a 128-bit identifier. Based on the 128-bit identifier, it will pick up the correct node where your key is present, right? So now go back and see. I have written a list of node that is responsible for storing a particular key is called preference list, right? And node that handles read and write is known as coordinator node. First among top n nodes in the preference list. If request received through a load balancer is not a coordinator node, then it will forward the request to the first of top n nodes in the preference list, right? So that is why I have left this point open, this diagram open. So now let's say, now by this time you understood then what is coordinator node and what is preference list, right? So coordinator node, don't assume that coordinator node is the only node which will basically do all the write operation. No, Coordinator node, let me explain you what is coordinator node. So now let's understand this with these boxes. Alright, so this is your N1. Let's assume that your N1 node has K1, K4 and K6. Okay, and then you have N2 here. This has your K7, K10. You have N3 here, and then N3 has K12, K15. Only assume 3 nodes, right? It becomes consistent otherwise. This is your client. It sends. So now by this time you understood by this diagram, each node has your keys, right? We use consistent hashing. So basically between these two nodes we will store these kind of range of keys, but we will understand that as part of the consistent hashing. For now let's understand that each node has some kind of data. So node 1 has K1, K4, K6, node 2 has K7 and K10, and 3 has K12 and K5, right? So this sends a get operation for K7, right? This sends to LB. Now load balancer rerouted it to, let's say, N3, right? So you see N3 doesn't has the K7, right? That means this is not the correct node. This is not the correct node to look for the data for K7, right? Because so it's not a coordinator node for K7 because it doesn't has the data. Now what the responsibility of N3 will be that it will reroute it to, so for each key, let's say K7, what will be the preference list? The preference list for K7 will be N2, and if this data, let's say, is right here as well, it will say N1. So these are the healthy nodes. So healthy nodes for the data K7 would be N2 and N1. So now your load balancer for getting K7 forwarded your request to N3, but N3 realized that it doesn't has the data and it's not the coordinator. I'm not the coordinator node for K7 data. So it will see, but in the preference list of K7 I have the N2, right? So it will pick up the first one from the preference list. So this is your preference list, and then rerouted that request to here. So now get K7 will come here, and then from here your request will be fulfilled. K7, right? So that's how it will work. That's how it will work in your load balancer. So that's what I was trying to explain at this diagram, right? So it's completed here, below down here. All right, and then this is your preference list. So for each key there will be some dedicated specific node. Let's say your data, your case K7 has been stored at node 1, node 2 and node 8, let's say. So your preference list for K7 will be node 1, node 2 and node 8. So this will be healthy nodes for K7. Now if load balancer picks up any node, let's say N5, so N5 is not the coordinator node for K7 will be N1, N2 and N8. If let's say N8 goes down, so coordinator node for K7 will be N1 and N2, because these nodes N1 and N2 can perform the write and read operation for K7. So that those are the coordinator nodes for K7. So that's the concept of coordinator nodes and the preference list, right? That's what I have written here. And then you understood that how your rerouting works during your get operation, or if it is a put operation, it will always perform a hash function on your key. Based on your key there will be outcome of 128-bit identifier, and that identifier will indicate a particular node. That particular node will be act as a coordinator node for that particular key. So any operation will be rerouted to one of those healthy nodes, and then those nodes will act. Since that particular node is a coordinator node, it will fulfill the request. And then strategies to select a node, a kind of two type. If send that request to a generic load balancer. Second, you use a partition aware client library. All right. So this all data, that facts and figures that I have tried to gather, right? It's not from a book, because I've gone through the paper published for AWS. Let me open that. Alright guys, so this is the paper that I have read in order to create these slides and gather all the facts, right? So you see even if you look at this part, right, this part, you see it has returned Dynamo treats both key and object supplied by caller as opaque array of bytes. It applies MD5 hash on the key and generate a 120-bit identifier, which is used to determine the storage nodes for responsible for the key, right? And then even if you see the replication, it says each data will be replicated to n number of nodes, that n we can decide, right? And the list of node that is responsible for storing a particular key will be known as preference list, right? So all this data, we have all this data based on this paper, right? And there are multiple things that we will go through all these operations as well. For example, if you look at the execution of get and put operation, right? So if you look at this, right, a node handling, look at this part, node handling for read and write operations, also known as the coordinator, right? And typically this is first of top n nodes on the preference list, right? I explained you the preference list, also explained you the coordinator node. And then second thing, if you see, look at this part, right? Both get and put operation are invoked using Amazon's infrastructure specific processing request over HTTP. Two strategies: one is route that request through a generic load balancer, or use partition aware client library, right? This part. Alright, so this all data, maybe I will make this paper published to I will add this paper to my GitHub repository along with this slide. You can go over this and understand it in the depth, right? But for now, let's move back to our slide and understand. So you don't have to read the whole paper. I have already gone through the paper and consolidated the fact and figure, and only within like 4 or 5 slides I will try to explain you the implementation of Amazon DynamoDB. Alright, so let's go back to our slide. Alright guys, so now let's move on, and then we understood the execution of get and put operations, right? We understood a lot of amazing things about DynamoDB. Now let's move on the techniques that DynamoDB use for many things. So one thing to understand is the high availability, we will understand, and then we will try to understand few the partitioning, handling temporary failures, recovering from permanent failure, membership, and failure detection. But before we go through this, right, understand these are big concepts, and I have not created any video for consistent hashing, vector clock, Sloppy quorum, hint and head off, entropy gossip protocol. We will create separate videos for it. I will be creating a system design course and putting everything into it, right? So but for now I'll give you a quick idea that what it is, and then we'll cover the topic, right? Now let's go back and then first of all cover the high availability part and understand how it maintains the high availability, right? So now let's say this is your N1, and then this is your N2, this is your N3, right? These are all connected, and then this is your client. So first, one way, now this is all leaderless, as I already told you, right? I have told you multiple times, then this is all leaderless, right? This is all leaderless. That means there is no leader. Now client sends your WX to write at node 1, but now let's say for some reason your node 1 is down, it's not available, server failure, right? So it's also server, it got failed, but now that write can happen to N2. That's one way, because right, or let's say if it's going to write N2 and your network partition happened, right? There is no connection between N2 and N3. Then later on, eventually the system will become consistent, because whenever N3 will be ready, we will handle that as part of the temporary failures, right? Or let's say the way this client and all those nodes have been connected, there is some network partition happened, and then you cannot write to N2, but you can always write to N3, right? Why? Because it's leaderless. As I said, there is no designated node. There is no node that you always have to write at this particular node, because it's a leaderless, right? You can perform the write operation at multiple nodes, right? It's not single leader or multi-master. So this is leaderless replication. That's the beauty of peer-to-peer architecture, or you can use the term peer-to-peer cluster, because it's a cluster, right? A cluster has multiple nodes, all those nodes are talking to each other, and how they talk, we will see that okay, it use gossip protocol to talk to each other, right? But we will understand that in later part. But that's one way it maintains the high availability. Second way, the way it maintains the high availability is, let's say you have N1 here, and then let's say you have N3 here, and then let's say you have N3 here, N2 and N3 here, and then you have client here, right? So in my last video, other two videos of single master replication and multi master replication, I explained you the concept of conflict, right? Because at the multi master replication, you always end up having conflicts, because let's say a client has returned the value of x is equal to 10 into your master 1, and but your master 2, the leader 2, also have the value of x is equal to 20. So the same value exists with multiple values for it. The data exists with multiple values for it. So that's a problem of conflict. But now the way many systems today, many systems, the way they resolve conflict is during the write operation, right? They resolve the conflict during the write operation. Let's say a client is writing here x is equal to 20, right? But x is equal to 10 is present, but at the same time. So it's a conflict operation. Now many client, what it does is resolve conflict during write. Or what happens, it will say okay, there is a conflict, so they will avoid writing the value of x, because it's a conflict situation. But no matter how they handle, the point is they always handle the conflict during the write operation, right? During the write operation. So that makes the system not available due for the write operation. But that is not the case with Amazon DynamoDB. Amazon DynamoDB doesn't do the conflict resolution during the write operation. It always do the conflict resolution during the read operation, right? So let's say you have this client, and this you have multiple nodes, 1, 2 and 3, and then this is your client. You have written already the value, but that's okay. But when you are reading it, and in the leaderless replication, you may read the value from multiple nodes, right? That's how your leaderless replication works. So if you are reading the value of x, the reading of value of x, and you see that there is v1 exists and then there is v2 exists, then during the read operation, you resolve your conflict resolution, right? So you will go back and say, you will go back to the client and say, for the x value we have v1 version, for the x value we have v2 version. Now you are basically exposing the conflict resolution to client and saying, hey, can you fix it? Which one do you prefer, v1 or v2? Based on the client preference, you can update the v1 or v2. But there are approaches, right? There are approaches. You call that approach is read repair. So as part of the read repair, what happens is, read repair will say, client will say, okay, there is version 1 exists for x, and then version 2 exists for x. What I'll do is, the node 1 is lagging behind, right? It doesn't have the updated value for x, because x has been already upgraded to version 2. So what it will do, it will send the write operation x for version 2 to the node 1, and then node 1 will also get updated. So that's the read repair in the your leaderless architecture to handle your conflict, right? During read operation, not at the write operation. And that's the beauty of Amazon DynamoDB, that makes it very high availability storage system. All right. Then there is partitioning, right? Which it uses consistent hashing. The point of partitioning consistent hashing is, so let's quickly understand this as well. You have nodes here, right? The system is connected. Now let's say the way you are using a function to you have a data, right? And then client is sending the data. Now you want to store that data to one of these nodes, right? Either this node, or this node. Now let's say you have this function which is dependent on the number of node, right? But again, that's a dynamic nature of distributed system. The one node can go down, right? what will happen, sometimes you have 2 nodes, sometimes you have 3 nodes, sometimes, point is you will have the n nodes at during a point, and during that, from that n node, multiple nodes can go down, multiple nodes can go up. That's the dynamic nature of the nodes, these servers. So if you have a function which is very much dependent on the number of nodes, that you will always end up rerouting your request to the incorrect node, right? So that's not the foolproof solution. That's where the consistent hashing came in. It says, okay, we have node 1, node 2, node 3, right? And then for your function 1, we will perform a hash function, and based the outcome, you will store the keys between it. Let's say you are storing any node. Let's say if your data is k1, k2, k3, we will store the data 1 or 2, between 1 and 2, right? So based on that function, you will find the data between 1 or 2, right? And then you might end up updating some data at this. So your data will be storing at this manner, right? You will be storing your clockwise. So you will always end up finding your key after a particular node. So that's the concept of consistent hashing. I'm going very fast, right, from the consistent hashing, because if I try to cover consistent hashing everything here, so this lecture will take hours, right? So what I'll do, I'm quickly covering it. So consistent hashing is a way of partitioning your data correctly. So you can add multiple nodes, or you can distribute the nodes more properly, right? And your separation or your distribution of keys among your server nodes will be much better, right? You also have a concept of virtual node, etc. You can Google around it. For now, till this lecture, till the time I create a separate video on consistent hashing. Second thing is sloppy quorum, right? And point is, we have hinted ahead of, right? So let's quickly understand what is quorum. The point of quorum is, let's say you have multiple nodes. Now you have node is equal to, let's say, 3, right? So this is the concept of quorum. So you have 3 nodes. Now let's say in 3 nodes, if you try to write the value of x, if your client sends the value of x at 3 nodes, right, there could be chances that one of your node goes down. Then your write operation will never be completed, right? And then if you are reading it, because you always read in the leader rest application from multiple nodes, if you are reading it from 3 nodes, there might be chances that one of your node has your stale data, because let's say this is node 1, this is node 2, this is node 3. During writing of x, your node 2 went down, so your n1 and n2 only has the x is equal to 10, and this has x is equal to 8, right? Now this was write operation. Now think about read operation. This sends rx, this also sends rx, this also sends rx, right? Now what will happen in this case? What will happen in this case? What will happen is, in the n2, n1 and n2 will send the value of x is equal to 8, you see, because it has the stale data. Write operation were never completed n2, right? And n1 and n3 will send the correct data. Why? Because the write operation got completed in n1 and n3. So you see, if we generalize this, so what I'll say, that you don't assume that write operation is completed when you are writing in all the nodes, which is equivalent to total number of nodes. What you do is, you only write at the w nodes. So I will say w is equal to 2, right? And I will say read is equal to 2. So at the minimum number of nodes to make your write valid, you only write at 2. You only assume that if your write operation gets completed at minimum 2 nodes, that means your write operation is complete. If your read operation is being done by 2 nodes, that means your read operation is complete. You don't assuming writing all the n number of nodes. So your overall equation should be r plus w should be less than n, right? Oh, sorry, not less than 10, it will be greater than 10, right? So this is your concept of quorum. All right. So now understand the concept of sloppy quorum. So if you go back, the concept of sloppy quorum says is, in case of failures, in case of network partition, when network partition happen at a large level, right? Now what will happen is, let's say you have these many nodes, 1, 2, 3 and 4. Now based on your quorum, if your now your quorum, you n is equal to have 4 and your write operation has 3, right? So based on the quorum. So now what will happen, let's say for some reasons your 3 nodes are not available, you only have 2 nodes available, right? In this case, what we'll do, either you drop your write request, you will say no, but nodes are not available because you minimum need 3 nodes to be available to make your write operation valid, but you will say no, two nodes are not available, so only 2 nodes are available. So as part of sloppy quorum, what it says is you only write at 2 nodes, right? So what it do, it will only write the X operation here, it will write X operation here. Now this second node, this is temporarily down, right? But at some point this node will come up, right? This node will come up. Now the same time when it will come up, this node which has taken the write operation on second node's behalf, it will send that operation here. So this process is known as hinted handoff. All right, this operation is known as hinted handoff, right? And not writing, just losing your write operation, rather than losing your write operation, you are writing in the whatever nodes are available, right? So this is sloppy quorum, and whenever your temporary node which went down comes up, that particular node which has taken the write operation, it will basically send the write operation, all those write operations to the N2 and say all these operations happened when you went down, right? So this is this process known as the hinted handoff. Now the last topic is your entropy and gossip protocol. For gossip protocol, you only understand that this peer-to-peer network, in the peer-to-peer architecture, all these nodes talk to each other, and understand that okay, this particular node is up or not. So each node talks to each other the way they talk to each other using a gossip protocol, right? And then last thing is entropy. Entropy is, if you go here and then you see you have node 1 and then you have node 2 and then you have node 3, right? So each node has some data, but so as part of entropy you have a background process here. So this background process keeps on checking for the lag. So let's say if this background process finds that, let's say this node you have N1, N2 and N3. Now because of some reason you completely lost your N2, right? And then it's a permanent failure. Then you added a new node, and then let's say this is N5. So this background process will say for each node N5 doesn't has all this data. So background process, this particular process will copy this data from all the nodes to your N5, right? So that is the concept of your entropy. So I have covered it all very fast, but you can Google around it, and I'll be making separate videos for it. In fact, I had to create all these concepts first, the videos on these concepts first, and then I had to create the Amazon Dynamo, but that's okay. I'll create later then, and you can always Google around it, right? And then understand all this topic, right? So in this video we went over what is Amazon DynamoDB, what is the basic characteristics of it, high availability and its eventual consistent system. It is the way cluster has been organized as peer-to-peer, and the way it update the data and persist the data is the key value pairing. And then the architecture of it, as I said, it's peer-to-peer. All these nodes are connected to each other, talking to each other via gossip protocol, and they understand that they also look at the health of each other, right, using gossip protocol. And then the way client writes to data is there are two strategies. One, sending it to generic load balancer. We understood how that will work, or client will use the partition aware library. Or second thing, whenever, no matter what happens, DynamoDB applies MD5, it applies a hash function on the partition key. Based on the outcome, that it maps that particular key to a server node. That particular server node which is designated for that key is known as coordinator node, and for each key you will have a preference list. That means those are the coordinator node which will handle read and write operation for that particular node, right? As part of your load balancer, if load balancer reroute your request to a node which is not the coordinator, then that particular node will reroute that request to the node which is the coordinator, and it will always look up to find the coordinator. It always pick up the first node from the preference list, and each node maintains a preference list. in the techniques we understood that the partitioning, the way the data has been partitioned is the consistent hashing, and it maintains the high availability using conflict during read, not conflict during write operation, and also the way the architecture has been organized leaderless. So even if there is a network partition server failure, always able to write the request. And then it avoid the way read and write has a quorum, and quorum of r plus w greater than n. I already explained you some time back. You can go back and understand. And then if the minimum number of r, or let's say w is not present, then but still it will write to whatever nodes are still present as part of w. So that is known as sloppy quorum. And whenever your node comes up, which was temporarily failed, it will send all the write operation to that particular node, so that the failed node will have all the write operations. So that's a hinted handoff. We also understood the background process, which will keep on looking for the gap in between the data of nodes. So that's comes as a part of entropy, and we understand all these nodes talk to each other using gossip protocol, and all nodes talk to each other and also understand the health status of other node, because all these node update a list of all nodes. So if any node goes down, it will understand, okay, this node will take out that node from the list, and then answer that there is a failure happened. So this failure happened in the membership. All this failure detection basically is being done at gossip protocol, right? So these are the internals of DynamoDB. I hope I was able to explain you. I gone through that paper. I'll upload that paper and this slide as well. And then if you are interested, you can always go over that paper. Otherwise, I have already consolidated the facts in these slides, right? So far we have covered everything about DynamoDB. Probably in next lecture we will come up with the MongoDB and understand the facts and internals of it. So thank you so much, guys. We'll meet in the next lecture.